Okay. Today, as I mentioned to you, I would like to make an exercise on decision making, because I think it helps a lot to get the feeling, the practical feeling, the feeling on how it works in practice. The exercise, it's here in my website, application of pairwise comparison for decision making. If you click here, you will get a zip file. If you open it, there are two files in it. And if you open the PDF, there is the text, which we can read together. Before I start the exercise, let me just tell you that I know that I am committed to prepare a trial quiz for you. Hopefully it will be done before Thursday this week. Okay, just give me some time, because I needed some time to prepare the questions. Okay, so this is the exercise. I'm reading the text, application of pairwise comparison to estimate the design flow of a hydropower plant. The text reads, a small hydropower plant with no regulation means that there is no accumulation of water upstream the withdrawal. A small hydropower plant with no regulation is to be designed for a cross-river section. The design flow can assume values of 80, 90, 100, 110, or 120 liters per second. So basically, you have a fixed number of options, and therefore your choice is to select the best one. Your decision is to select the best one. So it's a bit different from the exercise from the example that I gave you during the lectures, because in the example, you had to choose between 4 or 3, I don't remember, 3 different solutions: precise irrigation versus building a dam versus reducing the losses, the water losses. Here, again, the decision is to pick up one design flow among 5 different alternatives. Of course, if you get less water, you get less benefit from the withdrawal, but I guess you reduce the environmental impact, you reduce the impact on the ecosystems, etc. Conversely, if you increase the design flow, you get more benefit in terms of economic benefit, maybe, but also in terms of more water for irrigation, if the purpose is irrigation. But by increasing the design flow, you increase the impact. Okay, so after a careful assessment of the environmental and economic behaviors of the project, the following indicators or criteria, as you want, have been identified for evaluating the most appropriate alternative. The first is the economic benefit. We identify it with the acronym I1. The second is the impact on the fish community, I2. The third is the impact on the landscape, I3. And the fourth is the fruition of the downstream river reach for recreational purposes, I4. So these are the 4 criteria. So for each alternative design flow, you have to evaluate the value of each of these 4 criteria. How can we evaluate the value? One possibility that I mentioned to you is to use utility functions, and this is what it's used here. So for each of these criteria, utility functions are given. So let's read here. The utility functions associated to the above indicators, depending on the design water withdrawal, are piecewise linear functions whose coordinates are given in the following tables. So let's focus on the indicator 1, which is economic benefit. Now let me draw on the blackboard the resulting utility function that is given here. 1 second, I need to change the camera. So this is indicator I1. Let's write the corresponding utility function, U, with, depending on the design flow, QP we called it. And here we see that for design flow 0, we have utility 0. Remember that utility is varying between 0 and 1. Okay, let's see if you can read it. Yes. For design flow of 30, you still have utility 0. Let me see what is, okay, 30, I need to stay a bit here. 30 is still 0. So the utility remains 0. Why is that? Because probably there is a lower threshold such that if your design flow is lower than that, you don't get any economic benefit. Okay, because, for instance, the costs outweigh the income, and therefore the economic benefit utility is 0. And then for design flow 150, you have utility 1. So this is the resulting utility function, precisely. How it is evaluated? First, don't care about that, meaning that it is given and that's it. But the way it's evaluated is through an economic analysis, of course. And therefore, through this economic analysis, we determine that if the design flow is lower than 30, we don't have any utility. And we determine, second thing, that if the design flow is higher than 150, we don't get any additional utility. And this may happen, for instance, if you want to get water for irrigation, once that you cover the crop water requirements, then even if you get additional water, you don't use it. But if you get additional water, then it may happen that you have an increase of the cost. So basically, you don't have an increase of utility if your design flow exceeds 150. So through an economic analysis, you understand these details. And the third thing that you understand through the economic analysis is that there is a linear increase of utility between 30 and 150, from 0 to 1. It may be also non-linear, it depends on the case. Here, to simplify things, I describe the utility functions through piecewise linear functions. What does it mean, piecewise linear function? It means that the overall function is linear if you stay within each segment. So the change from design flow 0 to design flow 30 is linear. It's utility 0. It's linear. It's described by a segment. And then you have an interruption of linearity here because there is a bend of this curve, but then the function remains linear between 30 and 150. So it's a piecewise linear function. It's a function which is overall nonlinear, but it's assembled by the composition of individual piecewise linear functions. And the same for the other criteria. You see that the indicator I2, there is, again, a piecewise linear function, which is similar to that of indicator I1. The indicator I2 is the impact on the fish community, and therefore it means that in order to estimate this utility function, you need to analyze the dynamics underlying the survival and benefit of the fish community. So it's a completely different analysis, but of course it's possible to associate to each design flow a utility. And in this case, please note that the max of utility in terms of the benefit for the fish community is given to design flow 0, because we assume that the undisturbed situation is the optimal one for the fish community, because the fish community adapted to it, evolved according to it. And then for increasing design flow, you have a decrease of utility. And for design flow that is greater than 150, we give utility 0, which means that the fish community is severely compromised, and therefore it's a utility, a minimum of utility, and the minimum of utility is 0. I3 is the impact on the landscape, and in this case as well, the utility function has the max for design flow of 0. And then there is the fourth one is the fruition of the downstream reach for recreational purposes. Again, max of utility for design flow of 0. Now, we have these utility functions that basically what they do is to rescale in the range 0, 1 the assessment of the performances of each alternative in terms of design flow. How can we combine them? We combine them through weights. So the individual scores for each criteria are between 0 and 1. If we sum them through the weights, then we get for each design flow, for each alternative, an aggregated score to compare with that of the other alternatives. How do we assign weights? Through pairwise comparison. Okay, and so here we are done. The optimal river flow withdrawal, the optimal design flow, should be identified by using pairwise comparison, by making sure that the evaluation is consistent. Okay. Now, our job should then be now to make a pairwise comparison 2 by 2 of these 4 criteria. And we could also make it through a discussion among us. And, for each comparison, we should elaborate an agreed opinion. Or we can use, as a first example, a pairwise comparison that I may propose to you. Let's use this let's use this latter solution in order to be able to move forward quickly. Okay, now, first, let's move to R, which is our tool. I opened an R console. You know that I can't open RStudio here, okay? And therefore, I'm working on the console. I suggest that you keep working on RStudio, and then you have the console in RStudio, so you can just write what I am writing there, okay? And I suggest, if you can, that you follow me by repeating what I'm doing, okay? Otherwise, it's the utility of what we are doing, it goes down a lot. If you just look at the screen, it's not really useful as it should be. Okay, let's go then to the zip file again, and there is a proposed R code. We can open it, but please note that, if I made a cut and paste of this R code into the R console, it's done. But this is not what we want to do. And note that this code, let me increase it, starts with comments. I already mentioned to you the importance of these comments if you're working on a code. And also there is a reference to the example that we discussed during the lectures. The first thing that we have to do is to define the utility functions, to input them into R. And what I'm doing here, let's just take this first instruction and let's put it into the console. Copy and paste. The first instruction here, what is doing is to define the utility of indicator 1, economic benefit, for the design flow of 80. So let's look at the blackboard. Here we have the utility function. The utility function gives utility 0 up to a design flow of 30, and then there is a linear increase between 30 and 150. 80 is more or less here. It's 50 over, it's more or less here, 80. So what do we have to do? We have to estimate the length of this segment. This is what we want to estimate. To be estimated. And then this is U180, U180. And this is what I have to estimate. Okay. What is the length of this segment? The length of this segment is given by 1, which is the length of this one, 1 divided by 150 minus 30 multiplied by 80 minus 30. And this should be what's written there. Let's see. 1 divided by 150 minus 30 times 80 minus 30 is a linear interpolation. Correct? And this has to be done for the other design flows. So, what is the second alternative? The second alternative is probably, let me just check on the PDF. The second alternative is 190. Okay, so let me write on the console U190 is equal to 1 divided by 150 minus 30 times 90 minus 30. Okay, let's check. U180 is 0.41. U190 is something more. Okay, now let me go to the PDF again to see what is this following alternative. Is 100, 110, and 120. Okay, so U1, 100. Look, I went back to the previous instruction and I got it back in order to simplify things, okay, to speed up my computation. This is done. U1, 110. And U1, 120. Let's see the values 110, U1, 110, U1, 120. This is the way you should work, just without looking at the code that I propose. Write your code, and then you may check if everything is fine by looking at my proposed code. So now I go to it, and you see that it seems that everything is correct. Okay, the first utility function has been entered into R. Now we have to enter the other utility functions. Let me clear the console. We should repeat the same computation. It's just linear interpolation. Now allow me to copy the second utility function. U2. Copy and paste. By the way, you should have got an email this morning from the uni regarding the use of the masks. They are still required in the closed rooms. Now, don't ask me if this room is open or closed. I would say that it's closed, okay? There is a window open, but I would say that if the windows are completely open, then that's fine. But I suggest that you also make an effort. If you take the masks off, keep some distance, okay? Because this is also the same for me. If I keep that distance, I can take off the mask. But if I move from my table, I need to put it on. Okay. Now, this is the second utility function. Let's put the other two utility functions in. And therefore, at this stage, we have all of them okay. Just 1 second. Okay. Now, let's now aggregate these utility functions in a vector collecting for each design flow the 4 utilities just for practicality. Okay, it is at the end of the story, we have to sum the utilities for each design flow through the weights. So it's much better if I put already now the utilities to be summed for each design flow in the same vector. So U8 is a vector collecting the 4 utilities of the design flow of 80. And therefore, let me put here U1 80, U2 80, U3 80, U4 80. So this is U80. Now, let me put U90 now in the same vector. Look, I got back the previous instruction. I don't write a new instruction. I got back the previous one, and I just substitute 80 with 90. Okay, now 100. Now 110. And now 120. Good. I think we should be done. Now, let's have a look now at the sum with the weights, with equal weights, sum U80. What am I doing here? I'm just summing the utilities for each design flow, just to have an idea of what is the alternative that is getting the highest utility if I just take the sum without weights, or if you want, to give to all weights a value of 1, which is not really ideal because you know that weights should sum to 1, shouldn't have an individual weight of 1. So if I really want to get the result in the form of utility, what I should do is divide by 4. In this case, I'm giving to each criteria a weight of 25%, 0.25. So the design flow of 80 has a utility, an overall utility with equal weights of 0.6. 90, 0.56 is lower, 100, and lower, 110, lower, 120, lower. But we have to estimate the weights. By the way, once that you get a utility that is decreasing from 80 to 90, I noticed that it was decreasing. I immediately understood that if I kept increasing the design flow, the utility, the resulting utilities would be decreasing. Why? Because I am using utility functions that are linear and monotonic. They are not increasing or not decreasing functions, and therefore it's clear that once that I start decreasing, then this is what it happens. But if I made a different experiment, let's forget about, for instance, the impact on the fish community. Let's forget about it, okay? And therefore, what should I do for forgetting about it? Let me clear the screen. I should make a sum of let's start from 80. Of U81 sorry, I need to, okay, let's do this. U83, U80, sorry, U84, okay, and then I need an additional parenthesis here, C, divided by 3. This is the resulting utility. I summed the utilities of the first criteria, the third and the fourth, and I divided by 3. I had to add a parenthesis because I had to define a new vector, okay? And therefore I use the function C. Now let's see with 90. Still decreasing, but not really decreasing, not much. decreasing, but not much, not like before, because I removed a criteria that is, we can also, which is penalizing increasing withdrawal. Okay, always decreasing. So still the first one is much better. Let's try to remove another one. Like, let's use only the first and fourth criteria. You see that the utility is decreased a lot. 90. Still decreasing. Still decreasing. Here it starts increasing, so I have to correct what I said, because indeed there is some nonlinearity. The piecewise, the nonlinearity given by the piecewise linear function, it may cause a change of the tendency of the utility. Because I said I am using linear functions for utility. Actually, they are not linear, they are piecewise linear. So I'm correcting what I said. And you see that in this case, the highest utility is given to the highest water withdrawal. And you see what is the advantage of making an experiment, that you can elaborate your understanding. So I made a mistake when I said these are linear functions, because actually they are not linear. They are piecewise linear, but overall, as I said, they are non-linear. I made a mistake, and I realized my mistake by making the exercise. So you see that indeed making an exercise is essential for your understanding. I'm saying trivial things, but sometimes we really need to make an experience. And how did I realize it? How I improved my understanding? By just making some checks, which were not strictly required. I was just curious to say, okay, let's assume that the weights are the same, and let's see what happens. I was just curious to see. I played with it. And you see that playing with it allows you to gain a better understanding. And in practice, it allows you also to minimize the risk of errors, of mistakes, which is important for an engineer. It's extremely important, okay? Okay, and of course, if I take only the economic benefit, the best would be, again, for 120. This is a trivial experiment that I'm making now, okay? I already did it at the beginning. I already made this because I took the sum of... Okay. Now that we played a little bit with it, let's pass to the pairwise comparison. Good. So what we need to do now is we have 4 criteria. Let me pass to the blackboard. So we have I1, economic benefit. And we have I2, impact on fishes. Good. Now we have to compare I1 with I2. Compare. And we have to give a score. So is it, if I compare I1, the main term of comparison, economic benefit, with I2, impact on fishes, is it I1 strongly more important, it's more important, same importance, less important, strongly less important? And let's go back to the scores. Let's go back to the lecture, to the theory. Let's see what are the scores that we need to give. So, decision theory. Just 1 second, I go down. Here. Equal importance is 1. Moderately more important 3, strong importance 5, very strong importance 7, extreme importance 9. And of course I have to take the inverse if I want to say that I1 is less important. So, of course, if you ask the person who is taking the money, they will say 9. So I compare and score 9, okay? If you ask the fisherman will say score 1/9. Because this means that I2 is extremely more important than I1. If I put 1/9, it means that in terms of importance, I1 is 1, I2 is 9. If I put 9, it means that I1 is 9, I2 is 1. And between these two extremes, we can give any score we want. Any. And if you put 1, it means that they have the same importance. Is 1, 1. Okay. So what we have to do is to build the matrix that we know. So I1, I2, I3, I4. And the same here. I2, I3, I4. And we need to build this matrix. I was just 1 second. I need to add 1 column I1, I2, I3, I4. Okay. And here the same thing, but I don't have enough space, so let me just rewrite and compact it. I1, I2, I3, I4. Okay, now we are done. First, let's put the ones when we compare each indicator with itself. Clear? Okay. Now, let's try to build this matrix, a new one, okay? And then we will see what is the matrix that is proposed by the exercise. But let's try to build a new one, and let's try to understand consistency. And let's play the part of the people who really care about the environment, okay? So we really care about I2, I3, and I4, and we don't care much about I1, okay? And then what should come out is that if the matrix is consistent, we should express a preference for the minimum the minimum of the alternatives. Okay, so if I compare I1 with I2, let's put 1. Okay, let's say, let's remember what are the criteria. Impact on the fishes, I2. Impact on the landscape, I3. And impact on the recreational activities. Okay, let's suppose, first we need to elaborate an idea. So, okay, environment is more important than the economy, but what is more important here among these three? Let's assume that we care really about life and therefore fishes, okay? And then let's care that we care about tourists and a little bit less about the landscape, okay? We may say, let's look at life and people first, and then the landscape. Okay, so if we care much about fishes, then let's put 1,9 here, because fishes are really important. So let's give a score 9 to fishes. And then I3, it's the landscape. Let's put 1/5. Which means that landscape is less than fishes. Are you following me? Okay, good. And then we said that tourists are in between, 1/7. Okay. Now let's go I2 to I1. We said the inverse, so 9. Let's put all the inverses in the opposite positions. So this was I1, 1/3. Okay, so here it's 1/5. And here is 1/7. Good. Now let's look at the empty boxes. I2 with I3. We said that the I2 is fishes is more important. So let's give a score of, I don't know, let's try with 3, okay? Or let's put 5. And here we can put 3. Or no, it's I think it is correct in this way, because this is, yeah. Okay, I think it is correct in this way. Because this is, I4 is more important than I3, and then when I compare I2 with I3, I should give more importance of I2 with respect to I3, because I3 is less important than I4. So I think 5 and 3 is correct, more or less.
It should be 9/5. Or?
Sorry?
Or the I2 to I3.
You mean in the opposite positions, or no?
Instead of 5.
Oh, you could put 7 or 5 or 7 or 3. I mean, it's we need to check if the matrix is consistent later. Okay, let's take your suggestion. I wouldn't put 9 because I think it is too much, but let's take 7, okay?
No, the question was because I2 is 9 and 3 is 5.
I mean, it should be 9/5.
Yes, 9/5. Why is there only 5 and not 9/5?
You mean 9/5 should be like, okay, I understand. 9/5 is something like 2, correct?
Oh.
I didn't think about this reasoning. So you're suggesting that here I put 9/5. Okay, let's put 2 then, okay? And then there was another suggestion there, raised then.
No, the thing is, when we have the column, the I1 column, for the third and fourth position, we shouldn't have 5 and 7. Should be the opposite.
You mean here?
Yeah. 5 and 7.
Yeah, correct. Sorry. Yeah, correct. Yeah. This is what you were saying, sorry.
Yes, and if the priority for the fishing
Is that?
9, so
It shouldn't be the same, it should be the opposite, right?
Yeah, this is correct.
Okay.
This is correct. And here it was correct. I made a mistake here. So this is fixed, okay? And then, did you have a comment on this? Or because your suggestion, I misunderstood probably what you said. And I thought you suggested 9 over 5, so 2. I wouldn't say that. Let's put here 5 and 3 like my original proposal, okay? Let's see what happens.
So 1/5 and 1/3.
Yes,
Okay.
yes. It's I2, I3, so it's I2, I3, 1/5 and 1/3. Correct? Now we are just missing this one. It's I3 over I4, and
I4 is more important.
is more important, and therefore here, I don't know, 1/3 or 1/5. Let's try with 1/5, and then we put a 5 here, correct?
Yeah.
Okay, now we have to check for consistency. Okay, let's check for consistency, and let me look at my code because I don't remember my memory. You remember that we have to compute eigenvectors and eigenvalues for this matrix, and compare it with compare the eigenvalue with the order of the matrix, which is 4. So first, let's put into R this matrix. Okay, so let's define it. I borrow from my code. This is just a matrix with zeros. I called it prova, attempt, okay, in Italian. Now I have to fill it. So I think we don't have any other choice than writing prova 1 equal 1, and then prova 2 equal 1, prova 3 equal 1, prova 4 equal 1. Good. Now let's pass to prova 1 which is 1/9. 1/2, yeah, 1/9. Oh, sorry, I made a mistake. Just corrected it, okay? I just overwrote what I have written. Prova 1/3 is 1/5. And prova 1/4 is 1/7. Good. And now let's invert them. So it's prova 2 equal 9. Let me check, yes. And then prova 3 equal 5. And prova 4 equal 7. Are you following what I'm doing? I'm just putting the matrix in, and then we need to get prova 2. It's 9. No, sorry. Prova 1, 2, correct? Yes. And no, it's already defined. Sorry. Yeah.
2, 3.
2, 3. 2, 3, 5. Thank you. And then I can write 3 to 1/5. And then I need 2, 4. 2, 4 is 3. And then 4 to 1/3. Good. And then we just need to put 3, 4. 3, 4 is 1/5, okay, and 4, 3, 5. And then we make a check now because we want to make sure. Let's clear the screen. So let's see if everything works. Let's look at the integer. It's enough. It's 1, okay, 1957. Okay, very good. And then 5, 3 is okay. and then 5 is okay. Yeah, very good. This is the matrix. Now let's look at the code, how we can compute the eigenvectors. Okay, so this is the instruction. Let me copy it. So it's eigen prova, name of the matrix, symmetric equal false, because it's not symmetric, okay? So let's look at, I think the result is a list, name prova 1, values vectors, okay, very good. We have eigenvalues and eigenvectors, but in order to extract them, I need a subsequent instruction, which is, this is the instruction for the computation of the weights. And let's not question it, okay? It's basically, it's computes, takes the eigenvectors, and then only the first one, which is the right eigenvector, and then it takes the module of the eigenvector, of the right eigenvector, and then it rescales. You see at the denominator the sum of the weights. This is the rescaling. So the result is PESI. You see that the weights sum up to 1. If you make sum PESI, it's 1. Again, let's look at the instruction for the computation of PESI. It is taking the right eigenvector. You see that there is between squares, comma 1, which is the first one. It's the right eigenvector. And then it takes the module of the vector. And then the module of the vector gives the weights, but they don't sum up to 1. And therefore, I need to divide by the sum of the module of the vector in order to rescale. If you take a vector and you divide each element by the sum of the vector, you rescale it so that the sum gives 1. It's clear. You divide by the sum, and the sum goes to 1. These are the weights, but we didn't check consistency. And in any case, from the weights, you see that it comes out what we discussed here. The lower weight is given to the economic benefit, and then the highest weight is given to fishes, and then there is I3 and I4. I4 is more important than the I3, because you see that the weight given to I4 is more, which is tourism, is higher than the weight given to the landscape. It is what we are expecting, but now the question is it consistent? So let's check for consistency. And again, we need some instructions whose meaning you just have to take for granted, okay? Because we need to compute the eigenvalue of the matrix and compare it with the number 4. If the matrix is fully consistent, the eigenvalue is equivalent, it's equal to 4. It will not be 4, and then we have to evaluate consistency. So let's look at the code. So C1 is the max. What is the C1? First of all, let's take the max eigenvalue, sorry. It is this one, this instruction here. It's just an intermediate step. You see, it's 4.29. It's different from 4. Again, the instruction here is the instruction to get the max eigenvalue. Now, I have to compare 4.29. It looks not bad, really, but I have to compare it with 4. Okay, how to compare it with 4? Let's go back to the lectures here. I have to compute lambda max minus n, so 4 0.29 minus 4 and divide it by 3, and this is the consistency index. Okay, good. Let me go to R. This is, sorry, this was the max which I computed before. I have to take this one minus 4, and then let me put a parenthesis and divide it by 3. 0.09. This is precisely what is written in my code. Let me go to the code now. You see, it is assigned to C1. And if I make C1, it's 0.09. Very good. What is this? Go back to the lectures. This is the consistency index. But now I have to compute the consistency ratio, which is given by the consistency index divided by Ri. Ri is, as you may remember, a random consistency index, whose value is given here, 0.90 for a matrix with dimension 4. So what I have to do is basically to take, I go back to R, take this C1 and divide it by 0.9. The result is 0.11. And what is this? This is, go back to the lectures, it's the value of CR. If CR is less than 0.1, then the pairwise comparison is considered to be consistent enough. Okay, what is the result that we got? Yeah, it's just on the border, okay? So let's try to compute the result according to this. And then we make the break. And then in the next hour, we try to adjust a little bit this matrix, okay? Maybe that, we need to play a little bit with these numbers. You see that it's not very easy to be consistent because we made some effort, but we just hit the boundary. Okay, let's suppose that it's okay because you can compute the result anyway. You know that your consistency is weak, but let's compute it. And so let me go to the weights, pesi. Very good. And then what I have to do is to compute this sum. Let me see if I am correct. Sum U80 times pesi. This is the overall utility of the design flow of 80. Let's just, let me repeat it. Let me clear the screen first. These are pesi, and this is the vector U80, which is the utility given to the design flow of 80 according to each criteria. Now, if I compute pesi times U80, what I get is a vector of dimension 4, where each element is the product of the corresponding elements in the vectors pesi and U80. So you see that 0.41 times 0.3 gives 0.01. 0.77 times 0.5 gives 0.42. Do you understand? This is the product, element by element, of the two vectors. And then if I take the sum of it, the utility given to U80. Okay. Now, utility of 90. of design flow of 90. It's lower. Utility of design flow of 100. Again lower. 110. Again lower. 120. Again lower. This was the result that we were expecting because we gave really a low importance to the economic benefit, which is the only criteria where utility increases for increasing design flow. Now, a final consideration before making the break. The way we proceeded should be the way you work. You gain an expectation of the result. You elaborate an expectation, and then you make all the calculus, the computations, whatever, and you get a result. And then you compare the result with your expectation. If the result doesn't match your expectation, you should turn a warning light in your head, meaning that, why is that? Sometimes it's normal that you get unexpected results. And usually when it happens and you didn't make any mistake, it's a discovery. An unexpected result is a surprise. It's a discovery, which is a very good thing. But you should be aware of the risk. When you go against expectation, be very careful. It may be, there is high risk, high gain, okay, which is fine. It's maybe an opportunity. But when you go against expectation, and also in research, when we talk about discoveries, is when you get something unexpected. Okay, we can make a break and then we work a little bit on consistency. Okay, we take 15 minutes break. Sorry, I am a little bit late, and because I started 15 minutes late. Thank you.
Allora io vi capoviglio che il paese accanto quindi vado direttamente là, quindi compilo lo stesso il format, quindi offrire mail, perché c'era
Sì, perché bisogna fare l'assicurazione, quindi
no, ancora no, perché volevo prima parlarle, perché ho visto che...
Allora lo compili, mi mandi la mail quando l'ha compilato, d'accordo? Poi dopo se dopo do la posizione, comunque è stato bene.
Sì, ho capito dov'è.
Perfetto, allora ci vediamo poi là, poi dopo ve lo dico comunque, prima della gita vi dico le robe che vi posso fare. E quando compila il form mi mandi la mail, perché bisogna che stia attento a, perché in teoria saremo già altri termini, però vediamo che bene, prego, dai. Ho un sacco di amici a Pomiglia, ne parliamo poi durante la gita. Arrivederci. Ci sono 15 minuti.
Devo tirare avanti. Tirare a campare. Esatto, sempre quello.
Funziona?
No, sì, ma faccio un gioco.
هو بريزنت هتكوني
هو بعد سنة
بقول لك بقى
ولسه
Professor, excuse me. You could sample test about the examination individual.
Sorry, say again.
You could sample test about the examination individual.
Yeah, at the beginning of the lecture, I mentioned that I am a bit late, but I hope during this week it will be online.
Okay.
Thanks. Okay, so let's try to make an experiment to see if we can improve consistency. Let me try to put I2, 3. I am now trying to just 1 second. I'm now trying to change a little bit the matrix, and I want to try to change 1, 2, 3 to 7. I to 3. So sorry. Prova 2, 3. Let me put it to 7, and then 3, 2, 1, 7. So what I did is just to change these two elements of the matrix. I changed this one from 5 to 7. And this one to 1/7. Okay, let's see if we can improve, if we improved something. So first let's compute CI, C1. Let me see, C1, I don't think it improved a lot, but let's see. It is improved a little bit, not much really. And let me just, so let's move forward this way now. Let's now take the matrix that is given in the exercise, okay? You can play with the matrix, you know how to do it. So you can try to improve consistency. Let's try to get the one that is suggested in the code, which is this one. So first of all, it's the one in the diagonal, we can leave them. And let's take these, and then let's have a look at the matrix once that it's ready. Okay. So it is a matrix that gives it gives same importance to economic benefit and fishes. And it says that economic benefit is more important than the landscape and is less important with respect to the tourism. Okay, and then it gives more importance to. Here you see also some digits because we are not forced to use integers. I could put here in this example 6.5 or something like that. Okay, so let's stick on this matrix and let's see what happens. Let's compute the consistency again. C1 is more or less, I think it is the same. It is, oh no, sorry, here I forgot to compute. I made the same mistake before. I forgot to compute the eigenvector and eigenvalues. So this is why it didn't change the consistency. Then we could try later to see, to repeat the computation for this matrix that you see on the blackboard now, because I actually didn't do it. Do you understand that I forgot to? Okay, so let me clear the screen and let's now compute prova 1, which is the eigenvector and eigenvalues. Just 1 second. It's more or less here. Here it is. So now we can compute again C1. And C1 is, you see that it's better now. And then the consistency. Just 1 second. Now you see that it's highly consistent, but this is the matrix that is given on the exercise. Let's compute now the weights. Need to go back to easy. Here it is. So these are the weights. Okay. Now let's compute the utility of the design flow of 80. I go back, we already did this, so I just need to, here it is. Okay, 0.43, now 90. This is a bit lower, 100. Lower again, 110. Lower and 120. Okay, so again, in this case, the best is 80, even if we gave some more importance to the economic benefit, but actually probably the importance was not so high, and therefore we get this result. Now let me go back to this matrix here, and in order to do that, I need to get the definition of the matrix in its original form, and then I make the change that I made in the blackboard. So to get the definition of the matrix in the original form, let's look at the history, which I think it's the best solution. So let's put history here, and I'm not sure. So let me just, I can't go back in the screen here. So let me see. Let me see. Okay. Let's close this. And let me see if I make history 200. Okay, now. Okay. I don't know if it's possible. Let me check to see if it's possible to give an interval for the history. 1 second. And it's the help is here. Okay. File, load history, save history, okay. And then One second, I make a try. Okay, 9. Okay, let me make it short, so let's go back here, or let me just make an attempt in this way. Let me try to open them, but the history is not saved yet. Okay, let me try to make save history. And just 1 second. Now I try to open the history file. In this way, I can browse it. Give me 1 second. It's really slow, this PC. It's, let's try to close some window. Let me try again, because I don't really... Oh, okay, it is really slow. Okay, now documents are history. You see that I have the history file under documents, and let me open with Notepad. Let's see if I can, if I double click, no. One second, okay, here it is. So what I did is to save the history file, and then my working directory is documents. In the working directory, it created the history file, I opened it. And here I have the definition, all of my history up to today, and this is the definition of the matrix. So I take these lines of definition of the matrix. 1 second, okay. Very good. And I copy them and I put them into the console. Okay, so this is my matrix. Now, if I compute the eigenvalues and eigenvectors, which is this one, I should get the same consistency ratio, which was 0.1, let me see, 1. Yes, this is what I got before. Now let me make the change that I made on the blackboard, and therefore I go down in the history, and I think it is about here. It is these 2 lines here. Okay, I copy these 2 lines, copy. I put it in R. Now the matrix is changed. If we look at prova, you see that I changed it indeed. Now let's compute again the eigenvalues and eigenvectors and C1. It's more or less the same thing. It didn't change much. With this change, it didn't change much. It is a bit improved, but it's let's see. if I compute the consistency ratio, it's more or less the same. 1 second, I get back the instruction. This one, yeah, it's a little bit worsened. So maybe that instead of 1/7 here, I think the change was here, 7s and 1/7. Maybe that here I needed to put, before that there was 5, maybe 1/3. Let's see. So 3 and 1/3. Let's see what happens. I take these instructions back. So this is 3. And this is 1/3. Let's see computation of the eigenvectors and C1 and C1. Let's see. To compute C1, just 1 second. C1. I'm not sure I did this before. I didn't do that, correct? This is a little bit worsened, so let's do this. I'm going very fast because I'm making the checks, okay? Okay, 1. And then C1 divided 0.9. No, more or less it doesn't change much. So it is not really this one that matters. Probably we should work on the other, but let's forget about it.
Here, 3 and
Sorry? What is the mistake?
you wrote here 3 and 1, 3, but
No, he did the check for before. He did the check for the first one. No, probably we should change the E4 prop because it's the second one more important.
In 4 here.
No, EI4.
Ah, EI4, yeah. EI4. Let me see. So you mean, what is your suggestion?
Like.
Instead of 1/7, you mean?
No, instead of 3, we can put 5. No, 3 in the fourth column. Yeah.
Can you please tell me, because you said EI4, I didn't understand.
In I4.
I4, okay. Here, okay.
You don't put 3, but put 5 or more. You have a highest value.
So you would put here. No.
Second row. There.
Okay. Sorry. What is your suggestion? Let's try.
Probably 5.
And then it's this one, correct? Yeah.
Because it's the second one more important of what
Yeah.
we did on the assumptions.
Okay, so it's 2, 4. Okay. 2, 4, yeah. 2, 4, 5. And then 4, 2, 1/5. Okay, now let's try not to forget anything. And then C1. And then
C1 divided.
no. It is worse, but it is changed a lot.
Yeah. So is that the point?
so we can
put there 1/5 and 5 to the other. Change the numbers.
Yeah.
Are you sure 1/5? Okay, let's try. I don't think so, but let's try. I would say that because it is 5, before than that it was 3, correct?
Yeah.
Okay. I think let's try to put 2. Maybe that I'm not correct, but let me try it this way. I clear the screen, just 1 second, because otherwise you don't see anything. It is improved a little bit, and but I don't think we should. The final result doesn't change because you know it is not very very different. If it was highly inconsistent, then it would make a change. But I don't think we need. Let me try with the fractional numbers, but I don't think it is
Put 1.5, it's okay.
So one half, okay?
Yeah, and 2 in the other.
Yeah.
No,
Yeah.
amen.
I don't think, I think now it is improved a little bit, but I think we should work on some other number if we want to improve. But let's forget about it, okay? Because otherwise it becomes really, if you want to play with it, this is perfect. Okay, so I think we can close this exercise. Our conclusion was that we identified the best values. We did a couple of attempts. Good. Now let me close some windows. And no. Good. And let me go back here. Now, I think also this one is to be closed, and this one is to be closed. Good. Okay, give me some more minutes to now to move forward with the lectures and to take the next topic, which I want to discuss with you, is climate change and water resources. And this will be the subject of our discussion today for about 20 minutes, and then Thursday and maybe a piece of Monday also. Okay, a premise. This is a topical issue. Climate change is a topical issue. Just let me change the blackboard. Not the blackboard, the camera, sorry. Okay, this is a topical issue, and but on the other hand, it's not a matter for your exam. It's not something that I ask at the exam. And the reason is that, as you will see, it's mainly descriptive, and therefore I don't want to. I think it is already at the max height. So I don't want to add food for the exam. I just want to keep this discussion descriptive and try to get the feeling of why this climate change is important, and I think this is trivial. Why it's important, I think we don't need to discuss much. But what I want to discuss with you is the effect of climate change on the water cycle, because it is what matters to us. And as you will see, the moral of the story is that it's still unclear. And the fact that it's unclear means that for the purpose of technical design, there is a big question mark that is still open. How should we take climate change into account? This is something that always emerged in the past 20 years, because we started to be concerned by global warming basically at the end of the 90s. And since then, we still have this big question mark on how to quantify it, which means how to work in technical design by taking climate change into account. This question mark is still open. Of course, we made steps forward, but there is still this big question which always emerges, because climate change is very popular, is something that is very concerning. People are concerned, the stakeholders are concerned, and etc. And therefore, I think it is useful if we try to discuss the impact of climate change on the water cycle. And I give you this reference. This work page is continuously updated as soon as I get new information. First, let me say that I'm not an expert in climate modeling and atmospheric physics. You know what is my background, and you know what is my expertise. On the other hand, I faced the need of trying to fill this gap, and the gap is what I mentioned to you. So how to update our design practices to take climate change into account. And you know, it's a topical issue. On the other hand, it's something that I think we should define. What I mean is we should define what is our problem, what is our question. Our question is technical design. I'm not much interested because I don't have also the preparation to do that, to discuss the attribution, the problem of attribution of climate change. The attribution problem means what is the reason for climate change. And more than that, it means quantifying the drivers. So not only saying it's anthropogenic, this is obvious, but we also need to give a quantitative estimate of the anthropogenic influence over other possible drivers, because it's in the same way as it is obvious that climate change is anthropogenic, that humans are modifying climate, this is obvious, but it is also obvious in the same manner that climate is also naturally changing. We know that there were glaciations before than humans, and therefore we know that climate is subjected to change. So these are trivial things. The difficult thing is to make a quantification. So what is the influence of natural variability? 1%, 2%, 5%, 10%? Who knows? So what is the influence of humans? 80%, 90%, 99%. And you may say, well, why this matters? Actually, it matters because, you know, in order to solve a problem, you have to identify the causes. And as an engineer, you have to identify the causes in a precise way. It's not just enough for us to say, let's take a precautionary approach and assume that it's 100% human-induced. It's because what is precautionary for others, it's not precautionary for us. And I try to explain better. For the purpose of climate change mitigation, for the purpose of reducing CO2 emissions, of course it is precautionary to assume that climate change is 100% due to human emissions, because of course reducing human emissions is a no-regret solution. So, I mean, it is beneficial not only for climate, it is beneficial for the health of people, it's beneficial for the environment, for whatever. So, I mean, a precautionary approach, if we want to mitigate the human impact, is to assume that the human impact is 100% responsible of the problem at hand. But from the point of view of an engineer, the engineer has to design something in order to be resilient against climate extremes. Climate extremes are typical. I mean, it's something that happens. It happened already when the humans were not here. This is our purpose. In order to estimate the extremes, we need to identify what is causing the extremes. So if the extremes are not caused by CO2 emissions, absurd hypothesis per absurdum, I think the Latin is something like that. So if the hypothesis is that the extremes are caused by climate change, then, and it fails, it's not correct, or it's partially incorrect, it means that we are missing something causing the extremes, and that something is not taken into account into our design. And I give you a practical example. It seems that human emissions are not responsible for the duration for long-term droughts. The climate models say that if I increase the emissions, it looks like the climate predictions underestimate the duration of long-term droughts. So it happens that droughts that occurred in the past, like in Italy, in Europe, between 1940 and 1950, there were 7-8 years, I don't remember, with minus 20% precipitation. So it is something that happens. And climate models cannot predict that. So if I only stick on the climate models, on the interpretation that global warming, that CO2 emissions are the responsible driver for anything, I would underestimate the persistence of long-term droughts, which means that my approach, my design is not conservative. So when you are missing a driver, your design, for some reasons, may be not conservative. Still, climate models say that climate is going to worsen if we increase the CO2 emissions, and therefore a precautionary approach to mitigate the overall problem is to stick on climate models, but for specific problems, and the engineers always have specific problems, it's not a safe approach to simply assume that the output of climate model is correct. So it's not a safe approach to simply assume that CO2 emissions are responsible for any kind of extreme. And therefore, the attribution problem is important to us, but we don't want to get into it. It's not necessary, unless, we are working with a very specific situation. But I wouldn't get into the attribution problem. I would get instead on how to, I would stick on the question on how to obtain reliable predictions of future climate under climate change. This is the question. And I think that the starting point, in order to answer this question, is the analysis of the past climate. The starting point is to really understand the climate system and the extremes, how the impact of the water cycle evolved in the past. This is the typical approach of the engineer, to rely on data, to stick on data, analyze the data, and get a good knowledge of the current situation. And then you project this knowledge into the future. The approach of a person that is instead, whose mission is mitigation of climate change, is different. They don't need to rely on past data, because they strictly rely on models, because their approach is to avoid changes, to avoid big changes of the current situation. So the engineer has to understand the current situation in order to make prediction. And keep in mind that our understanding of the current situation is still limited. When we predict extremes, when we predict drought, when we predict floods, we are still limited, even if we didn't consider climate change. And our starting point is the understanding of the present. The mission of a person that wants to mitigate the climate change is to avoid changes, is different. So we have to make clear that our approach needs to be different, and for this reason I reaffirm that our task is to first assess the past. And it's an approach that is different from the approach of climate scientists. They are not really interested in studying the past. Okay, to some extent, yes, but not as much as an engineer. And another premise that I want to make is that the topic is controversial, and this is unfortunate. It's unfortunate because when there is controversy, solving the problem becomes more complicated. And you see that very often when there is controversy about a strategy, about a solution, there is a high risk that we don't do anything. And this is precisely what's happening for climate change. Actually, what we did so far, it's very limited. Okay, we took some action, but it's still very limited. And the reason is also controversy. And you see that the topic is highly controversial. Otherwise, you wouldn't understand why it's so popular. I mean, it's popular because there is still the need to convince people. Not as much scientists, but if we look at the statistics, they say that the public still has a limited perception of the importance of climate change. And I think that if we are in the situation, the fault is on the scientific part, because it's clear that communication failed in some way. Climate change is indeed important. It's important also to better understand our climate. We still have to work a lot on that. And it is important because if you see at the number of disasters that are currently happening, the major part of the natural disasters are disasters related to climate. So understanding climate is essential, it's important. But the perception of the public is not as high. The public is not so concerned about climate. And therefore, I think the fault is on the scientific part. It's clear that for some reasons we failed, and maybe that we failed also because we were excessively alarmistic. This is a criticism that is addressed to the scientific community. The scientific community started to make very alarmistic predictions 15 years ago, at the beginning of 2000, and there were announcements that in 10 years we would run out of water and we would have a dramatic increase by 2015 of the situation, and the changes that we observed were not so big. And therefore, maybe that this was the mistake, who knows. But actually, the result is that the topic is controversial. There is a lot of discussion. If you look at Wikipedia, you look on Wikipedia for global warming controversy, you see that it's indeed a huge controversy, and it's mainly related to attribution, what I mentioned before. So this is why I think it is much better not to discuss about attribution, because we should try to avoid the controversy. We are not interested in controversy. I'm personally not interested much in the attribution problem. It's not my task to devise strategies for mitigating emissions. It's my strategy it's our purpose to devise strategies for the adaptation to climate change. So let's make a big difference between mitigation and adaptation. Mitigation is that we try to reduce climate change. It takes a long time, usually. Adaptation is that we don't care in the positive meaning of reducing climate change, but we try to adapt to a changing climate. And this is something that can be developed, can be achieved in a shorter time scale. And it's typically a task for the engineer. Adaptation means that we have to make our water supply, our defenses against natural hazards more resilient. And it means that we have to design probably structures, or we have to design nature-based solutions, but it's a task of the engineer. And mitigation is something different. It's a task for economists because, reducing emissions has a strong societal impact. It's a cost for society, which is especially high for the people who are disadvantaged. And therefore, this is a task for political sciences, for economists, etc. So let's try to focus on the technical part of it, but let's identify what is the problem. So the problem is the greenhouse effect. I don't think we need to spend much words on that, because I think everybody of you knows what is the greenhouse effect. Let me just say that the greenhouse effect is not only caused by CO2, by the increasing concentration of CO2 in the atmosphere. It's also caused by other gases, like, for instance, aerosols, which are emitted by several human activities, and etc. So it's not only CO2, but CO2 is the most important one. And here you see a brief scheme, and there are also links here if you want to see what's some more details on the greenhouse effect. And now what is the result of this? The result is global warming. Okay, global warming is something that is, unquestionable. We are in a period of warming, whatever the driver is. So if we don't care about attribution, let's just focus on the reality. The reality, if you look at the glaciers, they speak clearly. We are in a warming period. How much? This opens some question marks. Data say that the increase of temperature from 1850, from the pre-industrial period, now it's about, in global terms, 1.2 degrees centigrade. The average temperature of Earth is about 14.5, I think. So there has been an increase in 150 years of about 1.2. And this implies, as we will see, an increase in sea level of about 15 centimeters. Keep the order of magnitude very clear, because this is something that it's not clear to people. Some people think that the global warming has been much larger, and the sea level rise has been much larger. So in terms of sea level rise, we talk about 15 centimeters, and global warming is about 1 degree. Strange enough, global warming was not constant from 1850. There were up and downs. In particular, there is, I think, a graph here. In particular, between 1940 and 1980, there was a stabilization, and then a sharp increase starting from about 1985. This stabilization with a decrease, because with respect to 1940, you see that there was a decrease of temperature, brought serious concerns, and in fact, on climate change. And in fact, the first concern was called global cooling. And if you look in Wikipedia for global cooling, you see the description. It's not clear why the temperature decreased after 1940, because it was during the economic boom after the Second World War. It is deemed that it was probably caused by an increase in aerosol concentration, which reduced the solar radiation, but it's not clear. And global cooling was a matter of concern up to the 80s, and some people thought that we were entering into a new glaciation. And there were several concerns because, global warming is concerning, but a global cooling would be even more concerning, because it is proved that the crisis period in the human history have been in correspondence of cooling periods. And it is quite understandable, because it has been proved that during cooling periods there has been an increase in the number of floods, in the frequency of floods, more rain, which means more floods, and therefore, for instance, the Roman Empire had its max prosperity during a climate optimum, during which the glaciers were much more reduced with respect to now. And then it seems that around 500 after Christ, there was a worsening of climate, and it seems that this was one of the causes of the collapse of the Roman Empire, because the Roman Empire was based largely on agriculture, and so the collapse, the worsening of the climate caused a decrease of food production. This is another concern. With a global cooling, you have a decrease of global food production, and therefore it looks like the Roman Empire had these problems. For sure, in the Middle Age, around 1300, there was a crisis in Europe, an economic crisis that was caused by a climate minimum. And we will see these up and downs of climate, natural up and downs that had severe consequences. So people were concerned around 1960, 1970 by this global cooling, but then global warming started. This picture is a bit controversial because it's based on measurements that are, they are the more pessimistic measurements, but I think it is a good example. And let me say that when you quantify the global warming, I said, and then I'm finishing for today, the global warming, I said 1.2. There is a difference if you measure the temperature from satellites or with ground measurements. And the reason is that urbanization has caused a sharp increase of the urban heat island effect. And therefore, if you look at the thermometers, the ground thermometers, it looks like from 1990 to today, the increase has been 0.6 degrees, 0.6, 0.7, which is a lot, because if you think 1.2 in 150 years and half of it in the past 30 years, it's a lot. If it continues with this pace, it's a bit concerning, and this is why people are talking we should try not to exceed 1.5, because 1.5 could be reached in 10 years. And but if you look at the satellites, at temperature from satellites, the increase has been 0.3, so half of it. There are several explanations for this. One is the heat island effect, possible heat island effect, even if some of the ground thermometers were corrected for it. Another one is that global warming is not homogeneous. If you look at this figure, you see that in the northern hemisphere, and in particular in the North Ice Cap, global warming has been larger than in the southern hemisphere. And the ground thermometers are mainly in the northern hemisphere, because in the southern hemisphere there is a lot of ocean. And therefore, maybe that indeed the global warming has been more pronounced in the northern hemisphere, which is a fact. In the northern hemisphere, whatever data you consider, you see the majority of the changes. Maybe because this is also due to urbanization, who knows? And there is a bit of uncertainty. But in any case, we are, glaciers speak for us. We are in a warming period. Okay, let's stop here for today, and see you on Thursday. We continue this discussion. Thanks.
Okay.